Okay, so refraction. Let's start with a drawing. Where do I want to put this drawing? Let's put it up here. Oh, there's something there. Let's put it here. Okay, so what we're talking about here with refraction is we have two different materials that light can go through. So let's do the easy ones, air and water. And we're going to hit this with a ray of light. Kind of like we've done 100 times before with mirrors and curved mirrors. We're just going to aim a ray of light at an intersection of these two surfaces. So just think of a fish tank, think of whatever it is, think of a light ray going from the air and hitting the water. Now, many of you have probably already seen this sort of thing. If you've ever been to like an aquarium or something else where light does weird things, like looking from the top of a tank, you see a fish at a place. Looking from the side of the tank, you see the same fish. It didn't swim away, but it visibly is in a different place. It's not any different than the demo we just did with the arrow. I just added water to a beaker, and all of a sudden, looking through it, the arrow switched. So maybe. Light does weird things. And part of that weird thing is because of this. When light goes from one medium to another, it will bend. Now, luckily for us, there's some physics here, and that will bend in a predictable manner. So we're going to learn how to, well, we're going to do the math, but how to predict and how to understand what exactly is happening. So we're going to need some structure to these drawings. Okay? And the first thing we're going to need is to talk about this intersection. Can anyone guess what we're going to name this?
Focal.
What's that?
Focal point?
Nope.
Focal line?
Nope. Where have we seen a line like this before with mirrors?
Normal line.
A normal line. A normal line. Now, normally, this normal line would be actually perpendicular. Now that I'm looking at it from further away, it doesn't look very perpendicular. It looks kind of crooked. Since we're on video, maybe we should try and make this right. Better?
I mean, not really.
Whatever. Close enough. We'll say. Okay, so we have a normal line, and now we have an angle. How should we, so that we can keep things straight, if you remember when we've done this before, which of these two angles for our incoming ray should we define and always talk about? The one by the normal line is correct. So let's continue labeling things. Let's call this our incident ray. And let's call this theta I. Theta is just going to be our representation for an angle, and the I is going to be, because we're talking about the incident ray angle. And you're absolutely correct. We are going to measure that from the normal every time. And now, we're not going to talk about exactly why yet. You're just going to have to, I guess, for the sake of right now, you're going to have to just trust. This ray is going to be bent. So this is our refracted ray. And again, we've got to choose how we define this angle. How should we do that? Yeah, so the same way we did. I'm going to run this line and talk about this angle from the normal. And again, this is just convention, right? This is so when we're talking about light and light rays and all this kind of stuff, to keep this consistent for curved mirrors, for refraction, for lenses, for everything else, we're always talking about that angle with respect to that normal line. And so this is the basics of refraction. When light goes from one transparent medium to another, the light will be bent.
Does it always bend in the same direction?
No. Well, sort of, yes. Let's just say it's predictable based on whatever those materials are. So it'll be consistent if it's like this, and we'll see what that means in just a moment. Everybody, so got this? Basics of this drawing. So like we've done with mirrors, you're going to draw that drawing a bunch of times. And so let's do some science definition stuff. I don't want what's below this visible, though. I know, we're getting there. So we need a thing. And the thing is going to be called the index of refraction. And this, to your point, is it the same every time? Well, sort of. Materials are going to have, or substances are going to have, an index of refraction, and that's what allows us to predictably assess what's going to happen with a ray of light going from one thing into another. Things are going to have what's called an index of refraction. It's a property of a material. And it just relates to how light bends when it goes from one material to another. And this will be one of the physics words, so there'll be a bookish definition of this too that's probably better than mine, but we'll let this one roll for right now. Okay, so I want you to put a chart, just a little quick data table, in your logbooks with some examples of some transparent substances for the sake of what we're going to learn over the next week or so. I guess 2 weeks since we have spring break parked in there. These are the ones we're going to use. Now, do you need to memorize these? I don't think so. I think I'll mostly give you these in the problem sets or the quizzes or whatever. So there's a formula for this also that you'll read in your physics talk. But the long story short here is, this relates to the speed of light in different substances. Now, to be fair, that's also a lie, but we're going to let it rip for the sake of high school physics. The light, we're going to say the speed of light changes, and that's what leads to refraction. Does it really?
That's it.
Liam?
The refractive index is 1 in air. What would it be like in a vacuum? Yeah.
Okay, all right, so that's a great question. So in a vacuum, in space, the index of refraction is 1.0, 0, 0, 0, 0. It's just the base speed of light. In air, it's 1.0000035 or something. Because air does slow light down a scotch.
So is there anything that's 0?
It can't be less than 1. So this is a ratio of, this is the ratio of the speed of light to whatever the speed is of your refracted substance. I don't think I don't think a black hole changes the speed of light. I think a black hole just has too much gravity the light can escape. the gravity well is too deep for light to,
I was just wondering if it would go like.
no, because it doesn't, gravity doesn't accelerate light like you're thinking, it bends it. But anyway, what is this telling us? What are these other numbers telling us then about those other materials as it relates to the speed of light within them?
That diamond flows the most.
Go break it down.
Why do you think diamond slows light the most?
Because it refracts it the most.
Yes, but that's circular. We're going round and round. Why does diamond slow light down the most? Because that's what this is saying, right? Air, light is almost full speed.
Because it has more molecules.
Water, it's a little slower. Glass, it's even slower yet. What about diamonds?
It does
Yeah, how do we make diamonds?
compressed carbon.
We crush what? Carbon. Coal is the same thing, right? We crush carbon down. So diamond is super, super dense, right? If you had a baseball-sized diamond, you'd be rich. For starters, you'd be rich. But secondarily, you'd find that that diamond is super heavy compared to like a glass thing of the same size.
No, you said density actually.
Diamond is a super dense material, yes.
Since you said like diamonds are dense, is it like the more dense
Yeah, but
something is, the higher the index
But
of
what you just
Yes.
said, you did not say.
Yes, which follows from this list, right? Air, and then water is a little bit more dense than air, and then glass is more dense than water, and diamond is super dense, yes.
Okay, so completely theoretically, let's say,
Theoretically.
like completely, I know this will.
Uh-huh. Yeah, it's going to break somebody.
You got a giant diamond,
Giant diamond.
about the size of this classroom maybe, and you shot a laser beam through it. Could you watch the laser go through it?
It's not, no, because it slows it down, but definitely not enough that you could see the thing.
Like, is that why diamonds are so strong? Because they're so dense?
Yeah, of course. How do you make a diamond? You take carbon and you compress it under heat and pressure.
Could I press it hard enough to make myself a diamond?
You could not, but that's how we make artificial diamonds.
So does this
We take graphite,
Yeah.
carbon, and we put it under lasers and pressure to push it down so you get heat and pressure and you smash it into a diamond, essentially.
So if I could get something strong enough to crush it, then I could take like coal from house.
That's literally, that's how we make diamonds. So if you ever buy, you would never buy. If you ever buy a diamond-tipped saw blade to cut, you use these to cut concrete and asphalt, like on a job site. The big giant saws that you see people walking around with, those are typically diamond crusted. There's little embedded diamonds in that material, and that's what cuts that stuff. So yes, they're super hard, but all those are made in the lab. Those are not natural diamonds. Yes, that would seem, and those diamond tip blades are expensive. Like a standard blade like this for those is hundreds and hundreds of dollars, even with lab-grown diamonds, right? So this is why these videos are so long, is because
We ask questions.
we end up with a tangent, and then I get downvoted on my videos because of all of you. So anyway, all right, so index of refraction. So now we have another thing. So let's go back to our drawing. And let's update our drawing just a little bit. And to update this, I'm going to put n of I equals 1.00 and n of refracted material, water, right? 1.33. I'm just going to update my drawing. I'm not going to change anything. I'm just going to update and label a couple other things.
What, are you trying to copy my paper?
I don't know what the actual...
Sorry, you just can't read it, I can.
So now we have our complete drawing. Let's see how we can make the math work out. So I told you this is predictable, and the index of refraction is important because this allows us to make some physics magic happen. Now that sounds very questionable.
That's how we made an arrow flip side.
All right, so the law of refraction, also known as Snell's law.
Smells like.
Snell's. It's an N.
Sorry, I'm like really good.
Snell's law.
I'm tired. I'm so tired.
Write down this formula. This will be on the board tomorrow. Ni sine theta I equals Nr sine theta R. Ugh. Gross. That looks really sciencey, doesn't it? Gonna go home?
I hate this.
Tell your parents, hey, I learned Snell's law today. Oh, that sounds interesting. What is it? Oh, it's Ni sine theta I equals Nr sine theta R. I know, exactly.
Sounds great.
Everybody will be so impressed.
Lorax.
It does sound awful. It looks awful too.
Imagine having that name.
I'm sure that's the scientist that came up with it. That's something I should know,
Fred Snell.
but I don't know that.
From the Lorax.
It's definitely Fred Snell.
Everybody here? Everybody got this? All right, so let's use it.
Fred Snell. It starts with an F.
Where am I at here? All right, so here is our thing. So let's find out what our refracted angle is. Boys.
Sorry.
Let's pick an angle for our incident angle.
His whole name is nuts.
I mean, this 45 would be a direct, so I'm going to call this 50. So we're labeling our drawing. We're going to update our drawing one last time and say that our incident ray angle is 50 degrees. And then we're going to use our brand new formula to find out what our refracted angle is. So you're going to need a calculator, and you're going to have to make sure your calculator is set in degree mode again. So you guys know how I do this. So Ni sine theta I equals Nr sine theta R. Ni theta I R theta R. Okay. I'm going to set this up like this. And now I'm going to start filling in the blanks based on my drawing. Now, your drawing is right on the page with you. I don't want to scroll. What is our index of refraction for our incident material? 1.00, right? It's air. What is our incident angle? We said 50. What is our index of refraction for our second medium? By the way, that's an index, so that doesn't have a unit. If you're wondering what the unit is for index of refraction, because you're dividing speed by speed, you don't actually get a unit. And then theta R is what we're looking for. So let's start plugging this in. Not it, Liam. So let's start plugging this into our formula, which is right there. What? We're just getting started. Okay, so let's start plugging this in. So I know it has been a hot minute since we, in this class, did any of this trigonometry, SOHCAHTOA stuff. But as a reminder, sine of some angle is just a number, right? Sine 50, when you plug it into your calculator, is just going to be some number. And fortunately, in this particular case, we're multiplying it by 1, so this math becomes pretty easy. What do we get?
For the total?
1 times sine of 50.
0.766.
766. equals 1.33. Okay, what's my next algebra step? Yeah, so we want to get this all by itself, right? We want to isolate our sine theta r here. So to do that, we get rid of the 1.33. What number do I get?
0.576.
Okay, so again, sine of something is just a number. But now we're in that spot where we need to get to an angle from a number. So we got to go backwards.
So sine is a negative.
Yeah, so this is where you're using that inverse sine trick. In your calculator, that's going to look like this. You do the sine thing. And again, this is on your calculator. Your mileage may vary. For the TI, Texas Instrument calculators, it's second and then the sine button. And then you're going to put in that little amount. And then what do you get?
3.7.
And again, if you're getting something funky here, make sure your calculator is in degree mode, not radians. I know you may, depending on your math class, you may end up with something different, but for what we're going to do in here, your calculator needs to be in degrees. So 35.2. Let's go back to our drawing. And that is the math for Snell's law. Now, obviously, I can make this much more interesting, right? We can do where you know the angles, guess what the materials are. Or you know one material and you know the angles, you don't know the other material, or so on and so forth. It also works the other way. So if your incident ray starts in something more dense and goes into something less dense, you're still going to get bending, but in this case it's going to bend away from the normal. And again, we'll do this with practice problems and everything else. We'll just keep going with the math. Questions? All right, I think we did it.